Have you ever just stopped and looked at the world around you, a solid chair, a definite table, and wondered how any of it is even possible? I mean, we know that at the smallest level, it's all just a chaotic, probability-fueled quantum soup. So how does our solid, predictable world get built from that? Well, today we're diving into one of the biggest, most mind-bending questions in all of physics.
So here's the fundamental problem, right? Quantum physics, our best theory of the very small, tells us that a particle can be in many places, in many states, all at the same time. It's called superposition. You've heard of Schrodinger's cat, I'm sure? Inside that box, the cat is literally both alive and dead. But when we open the box, we don't see some weird ghostly combination. Nope, it's one or the other. So what gives? How does the universe decide?
And this is really the great divide in physics. You've got the quantum world over here, which is this blurry haze of pure potential governed by chance. And then you have our world, the classical world, where things are definite. Things just are. For the longest time, physicists have been hunting for the bridge that connects these two completely different realities. To figure this out, a really powerful and honestly beautiful idea has started to take hold. And what's so cool is that it borrows a concept from a totally different field, biology. It suggests that there's a kind of natural selection going on, not for animals, but for reality itself. It's called Quantum Darwinism, and it was pioneered by the physicist Wojciech Zurek. And that name, Darwinism, is absolutely intentional. The idea is that the reality we see all around us isn't just a given. It has to actually fight for its right to exist. It has to win. So what's the big idea here? Quantum Darwinism says the environment, the air, the light, everything around a quantum system, isn't just sitting there. It's constantly poking and prodding, kind of testing that system. And only the most stable, the most robust quantum states are tough enough to survive all that scrutiny and make it out into our classical world. And these winning states, the super stable ones, they've got a name. They're called pointer states. You can think of them as the champions of this quantum competition. They're the properties, like the exact position of a particle, that are just so solid they don't get messed up by the environment's meddling. These pointer states become the building blocks of our shared reality, basically because they're the only ones that can last. Okay, so how does this selection actually happen? The trick is to stop thinking of the environment as just some passive background scenery. You have to start seeing it for what it truly is, a huge, nosy, and incredibly active participant in everything. Just think about it. Any quantum system is constantly being bombarded. Photons of light are bouncing off it. Air molecules are bumping into it. Tiny vibrations are shaking it. Every single one of those interactions is like a tiny spy or a witness that grabs a little piece of information about the system and runs off with it. All right, so let's walk through it. We start with our little quantum system floating in that blurry cloud of possibilities. Then it starts interacting with the environment. Now here's the magic trick. All those little witnesses, the photons, the air molecules, don't just look, they make copies, billions and billions of copies of the information they find. But, and this is the key, only the information about those superstable pointer states can be copied perfectly. All the other delicate, fuzzy possibilities, they get scrambled in the process. They're lost to noise. So what happens? The entire environment gets absolutely flooded with identical copies of information about just one state. That massively replicated superstable information, well, that becomes our shared objective reality. Now, if you've been following quantum physics, you might be thinking, hey, this sounds a lot like decoherence. And you're right, it's totally related. But quantum Darwinism takes things a huge step further. See, decoherence is great at explaining why we don't see quantum weirdness, why the blurriness goes away. But it doesn't really explain why you and I both agree on the same outcome. Quantum Darwinism does. It says not only does the blurriness vanish, but one specific, fittest state gets copied and broadcast everywhere for all of us to see. This is an amazing theory. It sounds great, but is there any proof? Does it really solve everything? Well, like any good idea in science, there's some solid evidence for it. But it also leaves us with some really fascinating new questions to chew on. And yeah, this isn't just some nice idea on a blackboard. There's actual experimental evidence piling up. In labs, physicists can use qubits, the building blocks of quantum computers, to actually watch this whole process unfold. They have seen in real time how information about a quantum state leaks out into its surroundings, creating all those redundant copies, exactly like the theory says it should. It's pretty incredible stuff. So quantum Darwinism has some serious points in its favor. It gives us this beautiful bridge between the quantum and classical worlds, and it's backed by experiments. But of course, it's not the final word. It opens up new puzzles, like why is a particle's position so often the fittest property that survives, but other things aren't? And it still doesn't quite solve the ultimate mystery of the measurement problem. What exactly is that final moment of collapse? So yeah, the debate is far from over.
So, when you put this all together, what does it mean for how we see the world? The implications are, and I'm not exaggerating, completely reality-altering. It suggests that this solid world we think is so fundamental really isn't.
Zurek, the father of the theory, said it perfectly. Classicality is emergent robustness, not fundamental. Just let that sink in for a second. It means the solid, certain world you experience every single day isn't the base layer of reality. It's a secondary effect. It's something that emerges from the deeper, messier quantum world, simply because it's the only information that's stable enough to survive. I absolutely love this way of thinking about it. Our reality is basically a quantum democracy. Every single time a photon bounces off something, that's a vote. And the state that gets the most votes, the one whose information gets copied over and over and over again, that's the state that wins the election. It becomes our shared reality. It's reality by consensus.
And that leaves us with one last, truly wild thought to ponder. Is what we call real just the information that's tough enough to survive being constantly watched by the entire universe? Is our reality just the ultimate survivor? It's a powerful, humbling idea that might just change the way you see everything.